Okay, let's dive into the incredible world of 3D metal printing. We're talking about a technology where you can build parts for jet engines or massive drilling rigs, literally from dust. But this amazing tech has a bit of a dirty secret. It can be ridiculously wasteful. Today, we're going to see how one crucial bit of research changed absolutely everything.
I mean, just think about that for a second. What if we could build these super complex, high-performance parts and only use the exact amount of material we need? No waste. That simple, powerful idea is the driving force behind the amazing work we're digging into today.
So, how in the world do you 3D print with something as tough as a superalloy? Well, the answer is in a technology that is completely revolutionizing how high-precision industries get things done. It's called Laser Direct Metal Deposition, or LDMD. Now, instead of taking a big block of metal and carving a part out of it and wasting all the shavings, LDMD does the opposite. It builds the part from the ground up. You've got a super high-power laser melting this fine metal powder, basically drawing each and every layer of a component into existence. It's what lets us create these wild, complex shapes and save a ton of material.
But here's the catch. Even with this futuristic tech, there's a huge challenge that's been a real headache for engineers and manufacturers. And it really all boils down to one simple, crucial question.
Right. Just because you're shooting a stream of powder into a laser doesn't mean it all sticks. A bunch of it can just bounce off or miss the tiny pool of molten metal. And when you're working with these exotic, super expensive alloys, every single grain of powder that doesn't make it is literally money turned to dust.
In the industry, they have a name for this: powder catchment efficiency, or PCE. Think of it like this. You're spray painting a tiny, priceless sculpture with pure gold paint. Every little speck of that gold paint that misses the sculpture and just floats away, well, that's pure gold wasted. That's exactly the challenge here. A low PCE means you are just blowing your budget away. And this isn't just about the cost. Low efficiency can actually create tiny defects in the final part, which can compromise its strength and its durability. Now, for a critical part in a jet engine or a deep sea drill, that is a risk you absolutely cannot take. And that's the problem these researchers decided to solve. So, how do you fix a problem like that? You can't just guess and turn some knobs. No, you need a scientific, totally data-driven approach to find the absolute perfect manufacturing recipe.
Now, this is where it gets really interesting. Let's look at the material they used: Stelcar 65. Just look at that composition. It's mostly tungsten. That makes it unbelievably hard and super resistant to heat and wear. This is the kind of stuff you use for turbine blades and hardcore drilling tools. It's an incredible material, but it's also incredibly expensive, which makes it the absolute perfect candidate for this kind of optimization study.
The researchers knew they had to focus on the two biggest dials you can turn in this whole process. First, there's laser power. Basically, how hot is the laser? Too little power, the powder doesn't melt right. Too much, and you can damage the part. Then there's scanning speed. How fast is the laser moving? Move too slow, you might overheat everything. Too fast, and you don't melt enough powder. It's all about finding that just right Goldilocks zone.
So how did they find that perfect combination without just doing endless, expensive trial and error? They used this really powerful statistical method. Think of it like they were creating a 3D map of a mountain range. But instead of mountains and valleys, their map showed them where the peaks of high efficiency were and where the deep valleys of waste were. By building this data map, they didn't have to wander around guessing. They could see exactly where the highest peak was and just go straight to it.
And after all that precise work and analysis, what they found wasn't just some small, minor improvement. Nope, they found a genuine breakthrough.
So here's one of the first huge insights they uncovered. Their model showed that while both laser power and scanning speed mattered, the speed had a much bigger impact on efficiency. It turns out that slowing the laser down just a bit gave the powder more time to properly melt and fuse to the part. And that little change dramatically cut down on waste.
And here it is, the golden recipe. After all that complex modeling, it all pointed to one single exact combination: a laser power of 1,850 watts and a scanning speed of precisely 7 millimeters per second. Not 6, not 8, 7. It's that level of precision that unlocks incredible performance. So, what did that perfect recipe actually get them? This number right here, 69.08% efficiency. Now, that might not sound like 100%, but for an exotic material like this, believe me, it's a total game changer. It means almost 70% of that super expensive powder is now becoming part of the final product. That can slash waste by a third or even more in some situations.
Now this number is just as important. The statistical model they built was over 98% accurate at predicting the real-world results. This is huge. It means manufacturers don't have to guess anymore. They can use this model to know exactly what they're going to get, which saves them countless hours and a ton of money on physical testing.
But these numbers, they're more than just data points from a research paper. They have real, tangible impacts on industries all around the world.
So what does this all mean for us? Well, it means the cost of making some of the most critical parts in our world just went down. It means less waste, which makes a high-tech industry much more sustainable. And for you and me, that means safer, more durable parts in airplanes and stronger, more reliable tools for our energy sector. It's a rare win-win-win. It's better for the budget, better for the planet, and better for performance.
At the end of the day, the biggest takeaway here is the roadmap. This research hands industries a clear playbook for how to get the most out of Stelcar 65. It lets them build better, stronger parts while saving money and precious resources. It's just a perfect example of how really smart, targeted research can unlock massive industrial potential.
And that really leaves us with a pretty exciting thought. Now that we can manufacture with this kind of precision and efficiency, what new doors does that open up? What parts that were once impossible to create can we now design and build? The future of manufacturing just got a whole lot more exciting.